Hi everyone, and welcome back. Today we're going to continue our discussion of one-factor or one-way ANOVA testing for the null hypothesis that the means of several different populations are equal to one another. In the last video we discussed how to conduct this test via the linear regression approach, but today we're actually going to just focus on the formulaic approach without the regression perspective behind this. So let's assume that we're interested in testing if there's a significant difference in the average customer service across different stores of a restaurant chain, where we're defining customer service as a numerical variable between 0 and 10. And let's assume we're going to survey, let's say, 3 different stores. So let's call these stores, say, Store A, Store B, and Store C. Now, you do not necessarily have to sample the same amount of values from each of the stores, but that's definitely going to make things a lot easier, and we'll discuss the pros and cons of having unequal sizes for ANOVA testing a little bit later. But let's assume from Store A we were able to survey 8.2, 7.6, 8.5, and 4.4 levels of customer service. In Store B, let's assume we were able to sample 9.5, 9.2, 9.8, 9.2, 8.5, and 8.9 customer service levels. And for Store C, let's assume we were able to observe 4.2, 2.1, 5.6, 1.8, and 4.3. So in terms of this particular setup, we are testing the null hypothesis that the mean customer service for stores A, B, and C are all equal to each other. So in this particular setup, we have K is equal to 3 different categories. So if we were to approach this from the linear regression perspective, that means we need to define K minus 1 or 2 dummy random variables for our particular model, where one of these stores, A, B, or C, would be our reference group. All right, so that's our basic setup. So to start, let us get some point estimates for these parameters mu A, mu B, and mu C. So one can find that x bar A, or the average of sample A, is approximately equal to 7.18, the arithmetic mean of the customer service for B, approximately 9.18, and the arithmetic mean for C is going to be equal to 3.60. And one can also find that the grand mean, so the grand mean, which we're going to be calculating via just the average of all of these recipients, is going to be approximately equal to 6.79. Now, one may ask, is this really the best way to approximate the mean? I just do the average of A, B, and C together, or is it better to average these averages together into one different average? We'll just briefly discuss this a little bit later. And also, it's important to note how many people we are sampling. So, of course, the number of people that we sampled in Store A was equal to 4, the number of samples in Store B was 6, and the number of samples in C was equal to 5, giving us a grand total of 15 respondents. So in order to calculate this arithmetic mean, this grand mean, that's just going to be the sum of all of those values divided by 15. Now, that's our basic setup. Now let's calculate our ANOVA metrics in order to conduct our ANOVA test. So the very first thing that we need to construct is what we call the total sum of squares. So our total sum of squares, right? So the total sum of the squares. So the total sum of squares in its formal definition is the sum from I is equal to 1 to k, so that's the sum across all categories of the sum from j is equal to 1 to the size of each of those categories of xij minus the grand mean squared. Okay? So in terms of how to calculate this, what are we actually looking at? So we're going to be looking at the value 8.2, subtract the grand mean, square it, plus 7.6 minus the grand mean, square it. Do that for all the categories in category 1. Then do it the same for category 2 and category 3 and sum up those sums. Okay? So one can actually show that this is actually equal to the variance of all the values times the total sample size minus 1. In that case, it's going to be 15 minus 1 or 14. And you should be able to find that that's approximately equal to 107.90. In terms of interpretation, you can talk about this as the total variation in my study, because I'm pretty much comparing all of my values to the grand mean. So the second metric that I want to calculate is what we refer to as our error sum of squares or sum of squared residuals, okay? So the formal definition is going to be the sum from I is equal to 1 to k, so the sum across all categories of the sum from j is equal to 1 to the size of each of the categories of xij minus the mean associated to that particular category of interest. So if I want to sort of describe what's going on here, let's go back to our table. So I'm going to be taking 8.2, subtract my 7.8 squared. Then I'm going to do 7.6 minus 7.8 squared. 8.5 minus 7.8 squared, 4.4 minus 7.18 squared. Add them all up, that's going to give me a number. Then I'm going to do the same for category 2, but instead of subtracting 7.18, I'm going to be subtracting 9.18. So 9.5 minus 9.18 squared, 9.2 minus 9.18 squared, and so on. And then lastly, I'm going to do 4.2 minus 3.60 squared, 2.1 minus 3.60 squared, and so on. Add up all of those sum of squares, and that's going to give you what we call our error sum of squares. Now notice if you look in this formula, technically we can actually rewrite this in a nice compact way. This can actually be rewritten as the sum from I is equal to 1 to k of the variances of each of those groups times the size of each of those groups minus 1. That's actually a nicer way to go about it, especially if you have Excel or R at your fingertips, and you should be able to show that that's approximately equal to 22.06. All right, so 22.06. And you can interpret this as the variation. So this is the variation within the groups, because I am comparing each of the values within the groups to their particular group mean. So that's the second metric that we have. The last metric that we need is what we abbreviate as SSM, or the model sum of squares. So the model sum of squares in its formal form is going to be the sum across all categories of the sum across all value in each of those categories of x bar I minus the grand mean squared. That is, I'm going to take each of the group means, subtract the grand mean, square it, and do that for each of the columns, right? Now notice that this formula does not have any j's in it, right? So technically I can factor this out of the sum, and I'm going to be doing 1 plus 1 plus 1 plus 1 nj times, right? So what I can do is I can rewrite this as what? So that should be ni, by the way. Ni, and that should also be ni, by the way. Let's just go ahead and fix those. Ni and ni. And this is actually going to be equal to the sum from I is equal to 1 to k of ni times x bar I minus x bar bar squared. Right? So that's a nicer formula that you could use to calculate the SSM. And using our example, you should be able to find that that's approximately equal to 85.84. In terms of its interpretation, we can interpret this as the variation between the groups, because it is focusing on the group means compared to the average of all of the values in our particular observation. So what we're doing here is we're taking the total variation and breaking it down into two subcategories, the variation within the groups and the variation between the groups, because the variation within and the variation between the groups should add up to the total variation. Now, generally speaking, for all ANOVA techniques, this equation is not necessarily the case. Later on, we'll look at some examples on when the SSE and the SSM do not add up to the SST. Okay, but at least for the sake of one factor ANOVA, so let's just formally state this. So for one factor ANOVA testing, even if the cells are not of equal size, the SST is always going to be equal to the SSE plus the SSM, right? And one could abbreviate this in a more compact way as T is equal to W plus B, right? Where T stands for total, W stands for within, B stands for between. So the total variation is equal to the within variation plus the between group variations. Right? So that's a nice little relation that we can use to maybe calculate 2 and quickly calculate the third, depending on your preferences. Now, these are not the metrics we use to calculate our test statistics, so we need 3 other metrics. So we need the MSE, which is going to be equal to the SSE divided by n minus k. So that's going to be the error sum of squares divided by the total sample size minus the number of groups we have. And then our MSM, our mean square error for our model, that's going to be equal to SSM divided by the number of categories minus 1. And the mean square error for our total, that's going to be equal to the total sum of squares divided by our sample size minus 1. So for our particular example, you can find that's approximately equal to 1.84, that's approximately equal to 4292, and that's approximately equal to 7.71. All right. So at least from these first two, we can calculate what we refer to as our F-test statistic. So our F-test statistic is going to be equal to the mean square error for our model divided by our mean square error for our error term. And for our particular example, you can find that to be approximately equal to 23.35, which typically is pretty large for an F distribution regardless of the degrees of freedom pair. And keep in mind, the F-test statistic for this one-factor ANOVA is going to be associated to an F distribution with k minus 1 comma n minus k degrees of freedom. So that means for our particular example, we're going to be associating this to a 3 minus 1, 15 minus 3 distribution, or an F212 distribution. So once you have our degrees of freedom pair and you've already calculated your test statistic, then you should be able to calculate an associated p-value for that. So the p-value for this is going to be approximately equal to 7.3 times 10 to the power minus 5. So that's 0.000073, right? Which typically is pretty small, right? So that's pretty small. Right? It's smaller than, for example, 5% or 1% or even 0.1%, right? So since that p-value is pretty small with respect to most alphas that people would choose, we're going to be rejecting the null hypothesis that mu1 equals mu2 is equal to mu3. So in terms of this rejection, how do we interpret it in terms of our example? That means at least one of these customer service averages is significantly different than the others, right? Now, can you take a guess at which one or which two or possibly which three are very different from the others? So if you look at our particular data sets that we were looking at, notice that we have 7.18, 7.19, and 3.6. So I would argue that this category or this store C, probably is the one that's causing the issues, but of course XA and X bar B are a little bit different from each other as well. So possibly all of them are different from the rest, right? But that's how you would conduct a one-factor ANOVA, where the factor we're focused on here is customer service between different populations. Now that we know how to conduct a one-factor or a one-way ANOVA for seeing if there's a significant difference between population means, now let us talk about a few concepts that are sometimes important to understand in regards to one-factor or one-way ANOVAs. So if the group sizes N1, N2 down to the last group size are all equal to each other, we say that the ANOVA is said to have a balanced design. If at least one of these group sizes is different from the other, for example, in our example, we call that an unbalanced design ANOVA. Generally speaking, the formulas for the balanced design are usually a lot more easier because, for example, that little ni term that was sort of hanging out in one of our sums, that could sort of factor out because they're all equal to each other and independent of that index I. But generally speaking, if you know how to do it for unbalanced, then of course balanced is a special case of the unbalanced formula. So one thing I want to look at here is the formula for x bar, right? So what is x bar bar in terms of our calculations that we're sort of comparing all our values to. So if you look at our formula for x bar bar, what we did was we took all our values regardless of the groups, so it goes all the way up to n, and divided by how many values we have in our particular sample. Now, if we focus this sum in the numerator in terms of the groups, then we can rewrite that as x group 1 respondent 1 plus x group 1 respondent 2 all the way out to x group 1 respondent n1. So that's the last respondent in group 1. And that's going to go all the way down to x group k first respondent, x group k second respondent, all the way down to the last respondent of the last group. Okay, and we can re-represent n as the sum of the group sizes. So we can represent as n1 plus n2 all the way down to nk. Okay, so if I have that, notice I can multiply top and bottom by the size of group 1. So divide top and bottom of the size of group 1, and I can multiply top and bottom of that by the size of group k, and do that for all of the values. And notice that this relationship, the sum divided by the sum divided by the size, is precisely equal to the average. So one can see that the grand mean is precisely equal to n1 times x bar 1 plus n2 times x bar 2 all the way out to nk times x bar k divided by n1 plus n2 all the way out to nk. So what do we have here? So the grand mean, so therefore the grand mean is just a weighted average. It's just a weighted average of all of the group means, right? Because we do not necessarily know which one to trust in terms of its value, so we pretty much weigh the one who has the largest sample size a little bit more than the rest, right? And we have seen this weighted type of structure, for example, the pooled variance t-test, pooled proportions, and so on. Now let's actually look at a particular special case for this. So note, if the ANOVA is balanced, what do we have? That means n1 plus n2, or n1, is equal to n2, is equal to n3, is equal to nk, which means all of the values are equally distributed across each of the k categories. Okay, so that means our formula for the grand mean can be written as follows. So that means x bar bar is going to be equal to n over k x bar 1 plus n over k x bar 2 all the way out to n over k x bar k, all divided by m. And notice everything is going to have a n over k in it, so that's going to be x bar bar is equal to n over k times x bar 1 plus x bar 2 all the way out to x bar k. And that's going to be divided by m. Notice that this n and that n will cancel each other, and that k will drop to the denominator. So that means for the balanced design, so for balanced ANOVAs, we have that x bar bar is going to be equal to x bar 1 plus x bar 2 all the way down to x bar k all divided by k. So that means the grand mean for balanced ANOVAs is equal to the average of the group averages. Right? Now keep in mind, if the groups are not balanced, the average of the group averages is not necessarily equal to the average of all the values. So that's an important thing to notice, but these two formulas are actually quite easy. So if your design is a balanced design, you can just find the average of each of the groups, divide by how many groups you have, that gives you the grand mean. But if your ANOVA is not balanced, you have to take all of the values, add them together, and divide by your total sample size, right? So those are just some interesting things to point out about the grand mean. Every time we're working with a hypothesis test method, for example the ANOVA, it's very important to understand the assumptions and premises for which that method is built upon. So remember, the last thing that we usually calculate in an ANOVA test is the f-test statistic, where an f-test statistic is a quotient of two independent chi-squared random variables, typically of different degrees of freedom. And remember, chi-squared random variables are built from normal or standard normal distributed independent random variables. So if we are not sampling from independent normally distributed random variables, then the test statistic may be extremely misleading. Right? That's not, of course, the only assumption that we are building the ANOVA upon. If you remember from our regression analysis, there's one very important assumption that must be met, and that is the homoscedasticity term for populations. So what does it mean for populations to be homoscedastic to one another? That means the variance of population 1, the variance of population 2, all the way out to the variance of population k are all equal to another or approximately equal to each other, at least in some statistical manner. So let's look at a few scenarios in terms of the equality of population variances and also how sample size differences may come into play here in terms of our analysis, and also the stability of our particular study. Right? So the first scenario is if all our populations are homoscedastic to one another, so sigma j squared is equal to sigma I squared, and let's also assume that the group sizes nj and ni are equal to each other, then that's great. That's actually the most ideal scenario. And you may be thinking, well, typically speaking, is it always possible to have equal sizes? No, of course not. And of course, we would like to be as large as possible in terms of the sample sizes, right? But actually, this is better than equal variances and unequal sample sizes, right? Which is case 2. So case 2 is if sigma j squared and sigma I squared and our groups are not necessarily of the same size, that's okay too. That's okay too. Right? So don't be sad if your groups are not the same exact size. If you have evidence to believe that the variances are equal to each other, that's okay as well. Now, scenario 3 and scenario 4 are, of course, the worst cases. So if our variances, sigma j squared and sigma I squared, are not equal to each other, and nj is equal to ni, it's bad, but not too bad, right? So it's sort of bad, but it's not the worst case scenario. So the worst case scenario is if sigma j squared is not equal to sigma I squared and the ANOVA table setup is unbalanced. So this is the worst case scenario in our ANOVA analysis realms. Now, how does sort of sample size play into this picture and why should we consider it? So let us recall what we refer to as statistical power. So statistical power, which we usually refer to as a probability of committing or not committing a type 2 error. Right? And usually sometimes we abbreviate statistical power via Greek letter pi. So the probability of committing a type 2 error, that's usually what we represent as beta, right? So remember, beta is the complement of the type 2 error probability. Right? And remember what we want about statistical power. Well, generally we want our type 2 error probability to be as small as possible. That means we want statistical power pi to be as large as possible. Right? That's a very important thing, right? Being able to prove things that are wrong, that's definitely an ideal case. Now, there's a theorem which we're not going to prove here, but it's very important to be aware of, is that the value of pi, statistical power, for ANOVAs is maximized or maximal when the group sizes are equal to each other, i.e., a balanced design. And that has to be true for all k groups, right? So once you start having groups of different sizes, you're actually decreasing the statistical power for this method to be able to pick up on any significant difference, okay? Also, let's assume, let's actually briefly review what we mean by type 2 error, just in case you don't remember what that is, right? So let's just briefly review. So remember, type 2 error is the probability of, or it's the event of failing to reject the null hypothesis, remember the null hypothesis says that these are all equal to each other, when this null hypothesis is actually false. That is, when we conclude our ANOVA test, that means we have evidence to believe that they are equal, but if they are not, that's what we refer to as a type 2 error. Now let's spin back into that little theorem that we said about if the ANOVA is of balanced design, then our statistical power is optimal, right? So let's look at a particular scenarios of, for example, good ANOVAs, bad ANOVAs, or the best ANOVAs possible, right? So what do we know about the sample size? So as we already know, ideally, the larger the sample sizes of the groups, the better, right? Because that usually decreases the standard error of each of our point estimates. So let's assume, for example, we have a sample size vector of, say, 15, 7, 9, and 17. So 15 in group 1, 7 in group 2, 9 in group 3, and 17 of group 4. So this is not good statistical power, right? But if we look at, for example, the another sample size vector, for example, if we have 15, 14, 12, and 16, this is not, let's actually call that n vector 1 and n vector 2. This is not good statistical power, but it's better than n hat 1 because the sample sizes are more close to each other. And there are some statistical tests to sort of see how spread out they are. Notice what metric would you use to sort of test whether the variance or the range is close to 0. Maybe you can sort of think about that and sort of see how to build a nice little test for that. But remember, good statistical power is when all the sample or our group sizes are equal to each other. So if we consider the sample size vector n hat 3, and that's, for example, 7, 7, 7, and 7, that is good statistical power. That is the maximal statistical power for which you can have for that particular sample size combination. But the sample size vector n hat 4, which is, for example, 18, 18, 18, and 18, also has maximal statistical power and has good sample sizes. Or I wouldn't say good sample sizes, but better standard error than n hat 3. Right, because usually as our sample size increases, our standard error approaches 0. All right, so just keep those in mind. Yes, if you have, for example, one of these categories, let's assume that you jump up to, like, for example, 100. So 18, 18, 18, 100. You're not gaining any statistical power in order to decide whether they are significantly different from each other or not. Just the standard error associated to that point estimate for, say, mu k is just a little bit lower. That's the only thing you're really getting out of that particular setup for unbalanced ANOVAs. There's one other thing that I do want to mention today, and that is what we refer to as the corrected sum of squares and the uncorrected sum of squares. The only reason why I want to sort of mention this now is if you're using some software such as SPSS, SAS, R, and sometimes even Excel, sometimes you'll see this word corrected or uncorrected next to your SST. So I just want to sort of briefly mention that just to sort of give you some insight on what's going on there. Okay, so this is just a side note, not super important, but it's interesting to maybe think about what it represents. So remember, the total sum of squares was equal to the sum from k to 1 to n. Let's actually represent this from the regression perspective because I think it's a little bit more easier to understand. It's going to be equal to yk minus y bar squared. So that's equal to each of the values in our sample minus the mean for which they all have, right? So this is sometimes referred to not just as the total sum of squares, but as the corrected sum of squares. Because notice that it's not really a sum of squares, it's a sum of squared differences, right? So the use of the word total sum of squares is not actually good. It's a corrected sum of squares. That is, we're subtracting the mean from each of the values which we are technically interested in squaring. So the uncorrected sum of squares, which is represented by the sum from x equals 1 to n of yk squared, is called the uncorrected sum of squares. Because if you do not correct this sum of squares representation for SST, then you're not going to get that nice little beautiful property that SST equals SSM plus SSE, right? So if that is the case, what is the relationship between the corrected and the uncorrected sum of squares? Because clearly one is hiding out inside of the other. So let's actually look at the SST and its decomposition. So SST, remember, is the sum of from k is equal to n of yk minus y bar squared. So if we sort of expand this via some algebra, that's going to give us the sum from k is equal to n of yk squared minus 2yk y bar plus y bar the quantity squared. And then we can distribute the sum over and then factor out each of the constants out of that sum. So that means we're going to have the relationship SST is equal to the sum from k is equal to 1 to n of yk squared minus 2y bar sum from k is equal to 1 to n of yk, and then plus y bar the quantity squared times the sum from k is equal to 1 to n of 1, right? So remember that that is just equal to n. That's just the same as y bar times n. So if I look at this expression, that's going to be minus 2ny bar squared, and then that's going to be plus ny bar squared, and then that's going to be, okay, so minus 2 cats plus a cat, that's just going to be minus a cat, right? So that's just going to be minus ny bar squareds. So that means we can represent this as the total sum of squares, I'm going to call it corrected, is equal to, because that's the uncorrected total sum of squares, right? So that's the total uncorrected sum of squares, and then we're going to have minus ny bar squared, okay? So we have this little difference from it, right? So what exactly is that? So this term has a few names, but I'm just going to give it a name just for the sake of giving it one. This is what we refer to as the mean correction. We're not going to get into the theoretical understanding of what exactly that is, but pretty much what we have here is that the corrected total sum of squares is equal to the uncorrected total sum of squares minus the mean correction. Okay, so that means the uncorrected total sum of squares is equal to the total sum of squares corrected plus the mean correction, right? So that's the difference between corrected and uncorrected total sum of squares, where typically we usually focus on the corrected version because we have that nice little property that SST is equal to SSE plus SSM. And sometimes we refer to this property as the orthogonality. This is the orthogonality property of the sum of squares. And if you're familiar with linear algebra, you may be thinking, well, I know what orthogonality means in the vector perspective. That means if you take the dot product between any two vectors, that's going to give us 0. So how does that sort of fit into this discussion? That's not something we will get into here, but do at least be aware that this property is called the orthogonality property of the sum of squares. So that is how we can actually go about doing a one-factor ANOVA test for a set of groups that are not necessarily equal to the same exact size for each of those groups, and also some terminology and concepts that you definitely should be aware of. So in the next video, we're going to be taking a look on how to conduct a two-factor or a two-way ANOVA test via both the classical and the regression approach. So I hope to see you there. Take care.